acceleration of energy. However, this is why the energy is far more powerful. Acceleration is not constant. Start out with very little acceleration. And then at this point, you've got a great deal of acceleration, no acceleration, acceleration that's upwards, acceleration that's downwards, and it keeps changing. Using the kinematics that we got from chapters 2 and 3, become a series of, well, we have to solve this problem, then that problem, then that problem, because the acceleration is changing, so we have to use such small segments that we'd be doing basically an infinite number of accelerations. In essence, calculus. But with energy, it's so much easier. I can figure out how fast it's going down on the bottom, because I don't care what happens in between, because it's frictionless. So at this point right here, what are the forces acting on the person?
Wait. Normal force. That's it.
All right. So I have these two forces. One's conservative, one's not. I know that my conservative work, or non-conservative work, is equal to the change in energy. So this would be my non-conservative force dot my displacement is equal to E final minus E initial. What is the non-conservative work being done?
The weight.
So what does somebody say?
The weight.
Weight is conservative force. What is the non-conservative work being done? All right, my normal force is this way. Which direction is he going?
That.
He's on the ski slope. Joey, yeah, it's going that way. So my displacement is this way, and my displacement is that way, my normal force is that way. They're perpendicular. When he's here, he's going that way, his normal force is that way. Perpendicular again. Here, perpendicular again. Perpendicular again. Everywhere along the ski slope, the normal force is perpendicular to the movement. Before, with the object falling, the non-conservative work was zero because there was no non-conservative force. Now it is zero because the non-conservative force is perpendicular to the displacement throughout the entire trip. So once again, we have conservation of energy.
Oh, I love this.
We'll make that 50 meters. Let's put it on the Earth 2. I have my initial kinetic plus my initial potential. See, we'll do my final kinetic plus my final potential. Oh, that was familiar. 1/2 mvi squared, 1/2 mv final squared. Initial potential energy. What's the potential energy associated with our conservative force?
0.
Looking for the formula.
MGH plus constant, but just MGH really.
There's a mgh initial. All right. This looks a lot familiar, a lot like the object falling. Mass cancels out, because I have this factor in every term.
And we're gonna come high, and we're going to set the initial height as equals 0.
Okay.
And then we solve.
And assume that he's sitting there, fat, dumb, and happy, and a gnat lands on his back, which gives enough impetus to get him moving. So initial velocity is close enough to 0. So we're left with the exact same problem we just did. So my final speed down at the bottom, is the square root of negative 2 g h final.
And then of course with one chunk.
Which is the square root of 2, negative 2, times 9, no, times 10, times negative 15. Which is the square root of 1,000, which is 31 point something.
Yeah. Because the square root of 10 is 3 point something.
Yeah.
31.62.
I have a question. So for the very first 1/2 mv squared initial,
Yep.
what, did we just say that was 0 because he just started there and just started going?
Yeah, he was traveling, he was.
It's like
basically
when we
arrested.
held the ball and then we just dropped it.
Yeah,
Okay.
yep.
And just this instance, he just started moving with no other force.
Yeah, I was that net landed on his back.
Okay.
We're currently in chapter 7.
Or 8. Wait, which book? 4, 5, 6. Yeah, that would be 7, I think. All right. One last very quick problem. I know you can do it, it might look more difficult. He gets out to the bottom of the hill, has a great time, decides to go back to the top. He goes back to the top here. He doesn't realize it, but there's been a cave in. Now down at the bottom of this, clouds, cotton balls and kittens. He comes zooming in here. Ah. He doesn't land on any kittens. But cats, sure, why not? Kittens, no. How fast does he go on right when he hits?
Right when he hits?
Yeah, or just before it makes contact.
31.62 meters per second.
Yes. The problem, from an energy point of view, doesn't change. His velocity is different. His velocity over there is more horizontal, velocity here is more vertical. But the speed is the same.
Not change. That's interesting.
The only difference in the, conceptually, is the non-conservative work is 0 along here because it's perpendicular to the motion. The non-conservative work is 0 here because there's no non-conservative force at that point. And they're apparently in the lesson.